as I was walking around, I noticed that a lot of you took that approach. Your first step here was to balance the equation. So you were looking at silver on the left and right. You were looking at nitrate on the left and right. You were looking at iron on the left and right. And you were looking at chloride on the left and right. One thing that I didn't see a lot of you doing was putting in charges. Now, in balancing, because this whole accounting thing, it doesn't really matter. This is just scratch work to help you get to the balanced coefficients. But then I noticed a lot of you going down to the complete ionic, but not carrying your charges in the complete ionic. It is important that when we go from saying something is aqueous ionic compound to its separated ions aqueous, we've got to start showing the charges. So here, it's okay to not show them, but why don't we talk about that first? Let's talk about the charges. Does anybody have the charge of silver memorized? Raise a hand if you have silver memorized. You've memorized something, but it's not the charge of silver. Okay, then we will figure out silver by working backwards. Does anyone have the charge of nitrate memorized? Raise a hand if you have nitrate memorized. A few of you. Okay. If you don't, that's okay. We can actually figure out nitrate later. Do you have the charge of iron memorized? Trick question. You can't memorize the charge of iron because it has multiple charges that it can take. Okay. How about chloride? You don't even need to memorize the charge of chloride. You just need to know how to use your periodic table. What's the charge of chloride? -1. Now that I know the charge of chloride, I know the charge of iron. This is, again, my box method. If I need if I need 1 iron to balance out 3 chlorides, then my iron must be 3+. Unit 2 material, right? Using chemical formulas to figure out ionic charges. Iron is 3+. Now that I know iron is 3+, I can actually look at how nitrate shows up 3 times, just like my chloride did. So what's my charge on nitrate? -1, the same as chloride. If nitrate had been a -2, it wouldn't have balanced with iron the same way that chloride did. It would have had a different chemical formula. So nitrate is -1. And now I actually have 2 pieces of information that can help me confirm the charge on silver. Silver is 1-to-1 with nitrate, and silver is 1-to-1 with chloride. What's the charge on silver? +1. It's really important to be able to determine these charges because there will be precipitation reactions, we'll talk about them today, where you're not given the products. You're given the reactants, and you have to look at how they swap counter ions, and you have to be able to predict the chemical formula of the products that form, which means you need to be able to identify the charges of the ions. Okay, silver on the left, 1. Silver on the right, 1. Nitrate on the left, 1. Nitrate on the right, 3. Iron on the left, 1. Iron on the right, 1. Chloride on the left, 3. Chloride on the right, 1. Here's the deal. I want you guys to practice this method over and over and over until it gets to a point where you're like, why am I wasting time writing this all out? I knew what coefficients I needed just by glancing. I've got 1 nitrate versus 3 nitrates. I need a coefficient 3 in front of silver nitrate. Can anybody justify for me why this needs to be a coefficient and why I can't rewrite the chemical formula to add additional nitrates? Alina? I just changed the chemicals. I can't say, oh, I'll just add extra nitrates in the chemical formula because now it's a different chemical, right? It's like saying, I'd like a peanut butter and jelly sandwich, please. Oh, okay. Here's a ham and turkey sandwich. Not the same. So I can't change the chemical formula, but I can change the coefficients. Okay, and that's what we would have recognized here. How do I balance 3 to 1? I need a coefficient 3 here. That changes nitrate to 3. It also changes silver to 3. And I have two things I can do. Now that silver is unbalanced, I can look at correcting silver, or I could keep moving down the line and I could try to balance chloride. It turns out those both balance in the same way. A coefficient 3 in front of silver chloride. Silver changes to 3, chloride changes to 3. But again, at a certain point, when you understand how this accounting process works, you would have seen 3 chlorides on the left, 1 on the right. A coefficient 3 will help me balance that right away. This is actually a balancing problem that I hope by the time you get to the unit test, you could solve in a matter of seconds without needing to show the work. But how do you get to that point where you can solve it in a matter of seconds? You've got to do the work, yeah? Anybody here play piano, read music of any kind? Did you take a lesson once and then read music the next day? How many times does it take reading music to actually be able to look at something and play it right away? It takes practice over and over and over. This is the practice. When you're doing real chem, do you have to do this? No, nobody checks for it. Nobody's grading you on the practice that you're doing. So when you're on real chem, have your notebook handy, do the work. Practice it over and over and over so that by the time you get to the unit test and the final, it takes seconds to finish. All right, I've balanced my complete molecular equation. But our goal was actually to get to the net ionic. Now, we talked in class about going from net ionic to complete ionic, from molecular to complete before getting to the net. Again, after you do this enough times, you may not need to write out the complete ionic equation. But let's write out the complete first. Anything that's written as aqueous is going to be separated. So I get 3 silver ions aqueous, 3 nitrate ions aqueous. And I want to touch on this. Why is it the subscript 3 from nitrate doesn't come out to multiply with the coefficient? Because we're going to look at how iron 3 chloride gives me iron 3 plus aqueous plus 3 chloride aqueous. Subscript 3 on chlorine comes in front, multiplies with 1 to give me 3 Cl minus. How come I don't take subscript 3 and multiply by 3 to give me 9? Anybody?
Is it because that 3 is part of that polyatomic ion? There's not parentheses around it, indicating that there's 3 of them. There's just 1.
Exactly. That is the polyatomic ion, NO3. So unless I'm going to break apart the polyatomic ion, I could say 3 times O times 3 and 1 times N times 3. But that would just be dissecting the polyatomic ion, and I don't need to do all that work. Taking this subscript out would change the chemical. Taking this subscript out gives me the chemical, yeah? It's not Cl3 1 minus, it's 3 Cl minuses. Okay, that's my left-hand side of my complete ionic equation. On the right-hand side, I have 3 silver chloride solid plus iron 3 plus aqueous and 3 nitrate aqueous. Can somebody name a spectator ion? Raise of hands. Alina. Nitrate, spectator, and iron. Spectator. Anybody want to define the spectator? How did Alina notice that those were the spectators? Didn't participate. They didn't change. Iron 3 plus becomes iron 3 plus? What? I'm sitting at a table with me, myself, and I? No, that's not a chemical change. Iron 3 plus is not in the chemical reaction. It's spectating the chemical reaction. Nitrate as well. Okay, here's the deal. Did we need the complete ionic equation to determine that? Could we have made that assertion from the molecular equation? Berkeley, you want to try and describe how you would have noticed it? Take out the ones that don't appear in the solid. Exactly that. Iron is a part of an aqueous solution on both sides. Iron will be a spectator. Nitrate is part of an aqueous solution on both sides. Nitrate will be a spectator. Silver and chloride will be a solid in the product. They have to be a part of the net ionic equation. Again, why do I want you to do this step? Practice. Get familiar with dissecting your ionic compounds. But after you've practiced it enough, you're going to get into a rhythm where you say, oh, look at this pattern. This solid in the product, those are the only compounds that show up in the net ionic equation. So be looking for those shortcuts. Recognize that once you develop these skills enough, you don't need to do all of the work. So after I remove everything, I get 3 Ag plus aqueous plus 3 Cl minus aqueous to give me 3 AgCl solid. Earlier I mentioned some of you were not writing your charges in the complete ionic or the net ionic that I was seeing. If you put 3Ag plus 3Cl, that's not correct. 3Ag plus, 3Cl minus. Those ions have to be present. Otherwise, you're telling me that they are elemental, that it's silver element and it's chlorine atoms, not ions. All right, if this is an option on the multiple choice test, and you select it, do you get points or do you lose points? Some of you are saying I get points, some of you are saying lose points. What's wrong with this balanced chemical equation? This is not the lowest ratio of whole numbers, the lowest ratio of coefficients. 3, divide all of my coefficients by 3, and the true net ionic equation is silver plus aqueous plus Cl minus aqueous gives me AgCl solid. Seems like a small thing, right? But that's what we're agreeing to. We're saying the balanced chemical equation has the lowest ratio of coefficients. All right, how did that practice feel? Getting a little bit more familiar with looking at these chemical reactions? Because one of the next things we're going to be doing is predicting products that come out of these reactions. Not just balancing, but predicting products and then balancing them too. Okay, 3 major types of reactions. Boy, this is really messy. The first one that we'll explore are these precipitation reactions. A solid forms from dissolved salts. Those of you in lab have actually done precipitation reactions already. In the very first experiment, chemical and physical changes, one of the things you did was mix together copper sulfate and sodium hydroxide, and you precipitate copper hydroxide. Now we're going to be exploring a lot more of them. The video that I showed on Monday, where it was several clips. It was a little water droplet and then these granules of salt dissolving into the water and then creating a new salt in the middle, usually with that new color. Those are precipitation reactions as well. Okay. One of the important concepts here is the idea of solubility. Solubility is defined as the amount of solute that can dissolve in a solvent. So solubilities have values. We say up to this much sodium chloride can dissolve in a solvent. We're going to talk more about solubility later and how we can change solubility by changing things like pressure and temperature. But for right now, we want to talk about two terms, soluble and insoluble. This feels very vague, but something that we call soluble generally has high solubility. What do you consider high solubility? Seeing as how solubility is an amount, that not really relevant at this point. Things that we call insoluble, they may just have a very low solubility. That doesn't mean that it's actually 0 ions will actually dissolve. It just means it's such a small amount of ions, it's basically insignificant. I do want to point out a tricky part of this. We would say silver chloride here is insoluble. That's why it precipitates and forms a solid, whereas iron nitrate stays aqueous. Those ions stay dissolved. By using the phase solid, I've seen students say or think that we're saying that it is soluble. So this is the part I want you to not trip over. If the chemical has S written with it, it means it's insoluble. In this example, silver chloride was insoluble. So how do we know if a chemical is soluble or insoluble? We follow solubility rules. Rules, yeah, because there is almost always an exception here. We're going to look at 4 primary rules. Things that are always soluble, things that are generally soluble, things that are generally insoluble, and then things that are basically always insoluble. So rule number 1, I'm going to write this out as kind of a fill in the blank, and we'll put in the blanks underneath it. In terms of like numbering the rules, this is not first priority, second priority, third priority. It's just numbers. And different people will number them in different ways. So if you don't want numbers because you think that's going to confuse you, just put bullet points. But these are the rules. Compounds containing these ions are always soluble. Nitrates, chlorates, acetates, and bicarbonates. You know what? I'm not sure why I'm making these plural. I mean, we can just call that singular. Are these anions or cations? These are anions. All of our 8s. Not all of our 8s. These are all 8s. All compounds containing alkali metals are always soluble. Are these anions or cations? Cations. And then also, all compounds containing ammonium are soluble. Writing the name is one thing. Knowing the chemical formula is the other half of it. So I want to fill these in. I want different people to give me different chemical formulas. First come, first serve. We've got a lot to go through, so I would like as many of you to participate as possible. Raise of hands, name one of these compounds and give me a chemical formula. First come, first serve. Nitrate, NO3 minus. Good. Ammonium, NH4 plus. Use your periodic tables. Okay, so you're right. Alkali metals are group 1. Do you want to give me one of them? Sure. Li plus. Good. Give me more. Raise your hands. Jacob. Chlorate, ClO3 minus. This is not perchlorate. This is not chlorite. This is not hypochlorite. Just chlorate. Give me more. Saint. Good. Bicarbonate. HCO3 minus. Different than carbonate. CO3 2 minus. Give me more. If you've got your periodic table, you've got a lot of group 1 metals you can give me. Na plus. One at a time. Raise your hands. You gave me one. K plus. Give me another. Who's got acetate? C2H3O2 minus. Good. I think you can also see acetate written as CH3, CO2 minus, or CH3COO minus. You'll see all of those different versions. Good. All right, let's round out the alkali metals. What else do we have? Francium. Anyone from group 1. Fr plus. Good. Rb plus. I put francium a little too close to potassium. What's my last alkali metal? Cesium, Cs plus. Seem fair? All right. Any compound that contains any of those cations or anions, always soluble. What phase will we give it? If you see a compound that contains bicarbonate, like sodium bicarbonate, do you give it solid, liquid, gas, or aqueous phase? Aqueous. Anytime you see any of those ions, that compound is aqueous. It does not matter what it's bonded with. Okay, rule number 2. Compounds containing these ions are generally soluble, except I'm actually going to put this as with exceptions, and underneath the ions will list the exceptions. Halides, except with, and we'll go through some of them, and sulfate, except with, and we'll go through some of them. Now here's another tripping point for a lot of students. They'll see a compound that has a halide, and they'll say, okay, that's generally soluble, except it's with these compounds, so that means now it's insoluble. But it's easy to flip it accidentally and say, oh no, the exception is that it makes it soluble. Yeah? So you've got to be careful running through these rules. And by the way, these are good rules to get familiar with and get accustomed to, but the ones you can't nail down, save a little corner of your cheat sheet for the final exam to have these solubility rules. Actually, I think some of them show up on your possibly useful equations sheet. Not necessarily all of them, but some of them do. Okay, can you guys give me the halides? Jacob? Not fluorine, that's a halogen, but halide, fluoride. Good, F minus. Another one? Chloride, Cl minus. Another one? Bromide, Br minus. And the last one? Iodide, I minus. If you're wondering why we don't go down to AT and UUS at the bottom of the periodic table, those behave more and more like metals than the halogens. So these are always soluble unless they're paired with, what type of ion do these pair with? Cation or anion? Cations. So these are always soluble except with the cations. Silver, Ag+, Hg2, 1+, Hg2, 2+. That's a diatomic cation, Hg2, 2+. And lead, Pb2+. Lead halide, insoluble. Silver halide, insoluble. Mercury halide, insoluble. All other types of cations with halides, soluble. Iron halide, soluble. We actually saw that before, iron 3 chloride. But we saw that silver chloride precipitated, insoluble. Sulfate, chemical formula. Is it SO3 2 minus or SO4 2 minus? This one's SO4 2 minus. I want you to recognize, remember, not all 8s have the same number of oxygens. Sulfates are soluble except with silver, mercury, lead. Ooh, it's kind of nice. 3 of them are exactly the same set of exceptions. But sulfate has a few more. Calcium, strontium, and barium cations. Ca2+, Sr2+, Ba2+. Didn't we say that all alkali metals are always soluble? Yeah, we did. And these are alkaline earth. This is group 2. But it's not all of group 2. Can you tell me what these have in common about group 2? These are all metals. They're on the heavier side of the metals. They're on the heavier side of group 2. So we notice we don't see it with beryllium and magnesium, but then calcium, strontium, barium. And we don't see it with radium. I don't think radium is very common, which is why it's not in this list. What do you think comes next in our rule? We've got always soluble, generally soluble, generally insoluble. Compounds with these ions are generally insoluble, with exceptions. Carbonate, phosphate. You know what? I'm actually just going to write this as a list. Carbonate, phosphate, chromate, and sulfide. Chemical formulas? I've still had some of you not participate yet. I'd love to get you to try and give a guess. First come, first serve. Sulfide is one that you can determine from the periodic table. You don't need to know the polyatomic ion. It's not a polyatomic. CO3, oops, what charge? CO3 2 minus. Bicarbonate, one of the minus charges is actually consumed by an H plus. So this is CO3 2 minus. One less H plus, one more negative charge. Phosphate, PO4 3 minus. Good. Chromate, you've got it? CrO4 2 minus. Reminds us of the sulfate, same charge, same number of ions, same number of oxygens. And sulfide, S2 minus. Good job, Mark. How did you know this was not SO3 2 minus? SO3 2 minus is what? Sulfite. Ite versus ide. The IDE tells you that this is actually a monoatomic ion, like fluoride, chloride, oxide, sulfide. All right, they're exceptions. Can you guys think of any ions that could bind with these anions that would make them soluble? Take that wild guess, Ryan. No. Okay, good guess, because you were looking at the exceptions here. No. Hydroxide's an anion, they won't bond with that. Alkali metals? Ammonium. So essentially, accept rule 1. Alkali metals and ammonium. We know they must be soluble with alkali metals and ammonium because those ions create always soluble complexes. Great. That's their only exception. Rule number 4. Now this one is actually just one type of ion. Compounds with hydroxide, again, I made it plural, I didn't need to make it plural. Compounds with hydroxide are generally insoluble. Of course, with some exceptions. Same thing as above, except with rule 1 cations. And this one's going to feel kind of odd. Now, Ryan, you made this guess earlier. You said, you know what? I had these pairs of exceptions, silver, mercury, and lead. They were exceptions for both the halides and the sulfates. So maybe that same set could be an exception here for the hydroxides. It actually won't be. But it will be another common pair. So rather than these 3, the exception for hydroxides are those heavy group 2 ions. Calcium hydroxide, strontium hydroxide, and barium hydroxide. So I do want you guys to notice kind of this helping hand in the trends. All of these exceptions show up twice, and no more than twice. These 3 show up twice in 2 different exceptions. These 3 show up twice in 2 different exceptions. So now we know. We can look at an ionic compound and decide if I drop this in water, will it generally dissolve or will it generally not dissolve? This is what we could have done earlier when we had that chemical equation. Silver nitrate plus iron 3 chloride forms silver chloride and iron nitrate. We could have started there and said, I don't even know their phases. I'll use the solubility rules to determine their phases. Silver nitrate, soluble or insoluble? According to what rule? Rule 1 says nitrates are always soluble. All right, now somebody else. Iron 3 chloride, soluble or insoluble? Are you looking for iron? You're not going to find it. So look for, good. Chloride, generally soluble. Is this an exception, iron? No. So it's soluble. Okay, now if I told you that those are your two ions, you've got this ionic compound and this ionic compound, what are the possibilities of what they could form? Well, I have silver, and I have the possibility of silver and iron coming together to create AgFe4+. No, that's not a possibility. Salts are neutral. Ionic compounds are electrically neutral. These don't balance each other. It's not a possibility. I could also have silver and nitrate come together. That's not different. That's the same that I had in the starting material. That's not one of my options. What's the only other possible combination? You know what, actually for the same reason, I could say, what if two silver ions come together and I get Ag2+. Again, not a salt because it's not electrically neutral. What's my only other possible combination of ions here? Silver and chloride, AgCl. That is a new combination from my possible ions. I've actually solved for what Ag could create, and I've solved for what chloride will create. Now I just look at the remaining ions, iron and nitrate, and that's my second compound. Silver chloride, soluble or insoluble? According to what rule? Yes, silver chloride is the exception to Rule 2. Insoluble with silver. Iron 3 nitrate, soluble or insoluble? According to what rule? Nitrate is always soluble. So now you don't need to just be handed the phases, you can determine the phases themselves. Okay, here's how I'd like us to spend the next 10 minutes or so. You and a partner are going to work together to create two ionic compounds. I want them both to be soluble. Then you and your partner are going to trade ionic compounds with another group. Okay? And you are going to solve for the precipitation reaction that might form. Pick two soluble compounds. Trade with another group. And predict the product of their reaction. You could also solve the product of your own, but that's not the trick here. Okay, truth be told, there are ionic compounds that you can mix together that do not give a precipitated product. There are compounds that you can put together in solution where no matter what, all of the possible combinations are always soluble, and that will not give a precipitation reaction. That's important to be able to recognize as well. Does this activity make sense? Okay, now unfortunately I'm not going to let you do this on your own. I'm going to assign you into groups. So just for the next 10 minutes, I want you guys to just be able to kind of move around. Maybe take a scrap piece of paper with you so that you and your partner can determine ionic compounds you want to work with, and then be able to solve for a precipitation reaction. I know this is going to feel a little weird. Here's how I want us to do this. I want you guys to line up kind of maybe like through the middle of the classroom from tallest to shortest. All right? And I'm going to assign you into pairs, and then I'm going to tell you, actually, you guys will be able to find another pair to work with when you're ready. All right? Tallest over here on my left, shortest over here on the right. Yeah. You guys can kind of be in the middle unless you want to show up on the camera, like through the chairs. You know what, I'll just pause it. Predict. Pick two compounds. You're going to create two compounds, any combination of your ions that you want. And it doesn't just have to be ions on here. It can be any ions. We noticed iron's not on here. Any compound you want, but those two compounds need to start out soluble, so that you can imagine getting soluble solutions in the lab and then dumping them together. And it's going to feel like this. You're going to pick two compounds you know that are soluble, and then the other group is going to have to solve what they form and whether they precipitate or not.
Wait, so we're not solving?
You don't need to, because you're going to solve theirs, but you're welcome to if you want to. Now you find a group, yeah. So stand up so when you're ready, so that other groups know that you're ready as well.
All right, let's go. What did you guys say? We did FE and O3. So we did
Fe and O3 is not compound. That would be Fe plus. But it's got to be Fe2 plus or Fe3 plus.
Okay. Does copper sulfate plus?
Sure, that's going to change your chemical one.
I just pulled it from the example from yesterday.
Guys, copper sulfate is yeah, soluble. Fe NO3 2 or Fe NO3 3.
Is anyone else ready? That's two right there. What you guys got for us? Here.
Kind of want these. So you guys know.
So then we're predicting.
Okay, so
They're all. Are you adding these two together? Okay, so it's like yeah, like that's how I do it. Whatever that says.
I'm not moving at all. Yeah, these are good starting.
I guess the.
Oh no, this one. Yeah. Sorry. This works great. Now we'll find another group.
So that would be
It's going to be one of these three. I'm not sure if these guys are ready. You guys ready? You You need more time? You guys ready? Alright, so you two are gonna work with those two when they're ready, when you're both ready. Maybe you two with them.
I don't know, the way that I do this, the way I go to it, I just flow through.
What do you guys feel? Yeah? Can I put some of your examples up here on this board?
Sorry, that's 1 minus.
Jordan or Amir, what was your compounds? So you gave these to each. NaCl plus okay. And we know these are all aqueous, but we'll come back and talk about it. You guys swapped already? Yeah. And are you working to solve it now? Okay. Just put them up there so we can kind of look at them together in class too a little bit. Okay, what compounds did you guys give them?
Do we balance and balance charges first before we start going?
Okay. Mix with.
Before we start going through this balance, you have to first balance, that's what you did. So you just brought back the two of the columns and plus two.
And what did they give them?
NaCl plus copper sulfate.
Copper sulfate. Copper 2 sulfate.
Yeah.
Okay, good.
Yeah.
And then for this, so you put the metal first, and then there's the metal. Plus
After you swap? Sure. Yeah, you can work together if you want to. You're going to be solving for the products formed and whether there's a precipitation.
Right. But the charges are. Do we need to the charges have to be balanced? Do the charges need to be balanced?
Always. Ionic compounds have to have balanced charges. Yep.
Okay.
That's just predicting the chemical equation or the chemical formula of the ion.
Okay. So iron has to be a plus 2. So we need copper Cl2. He probably positive. So we're actually balanced, right?
Right.
And then it has to be 2.
Yeah, kind of. So you've got a compound, you've got these two, you're going to try and predict the products. I think these were there. So that's not the products form.
Okay.
So you're going to say what forms from these
Wait, why would you put this one? But you first write it like this, and then you put the two.
Yeah, but the charges
Question. So when you're balancing these out, and you said that we needed a 2
Okay.
balance out the -2 from the columns on this ion.
Well, that's a -1. Nitrated. Nitrate is always
Yeah.
because there are two of them. 2 -1
Oh.
that balances 1 plus 2. Yeah. Well, the sodium and nitrate are 1 plus and 1 minus, so they balance 1 to 1. It's true they balance 2 to 2, but we need the lowest ratio of those subscripts for ionic compounds. So it would be NaNO3.
Oh.
Good. That's it.
And do we have to determine that?
Yes, you do. Yep, you're going to determine whether any of them precipitate or not.
So yeah, that's why if we mix it,
You guys gave them H2SO. Oh, I missed that. Potassium sulfate? Yeah, it can exist for sure. Okay, good. I'm gonna write something down here. No, I already forgot.
this is the nitrate. So that it has to be
Right, using rule one. So yeah, so it would be plus NA.
Yeah, give me
Okay, and what did they give you? Okay.
well, I mean not in volume.
Calcium, iron, chloride, and C+2 on it.
I'm gonna try our own, just so
All right.
I actually practice.
We're gonna do like a 5-minute break right about now. So if you're kind of in the middle of it, feel free to also partake in the break, because when we come back, we're gonna solve all of them together anyways. But take this opportunity to get up and do a little bit more moving around, and we'll finish all of these in 5 minutes. If you aren't gonna take a break, I'm happy to answer questions.
I have another question. So now I'm trying to an example. So now I'm trying an example, and this is really easy.
Mm-hmm.
And figured out what my or
Yes.
so that means that this would have to be positive, right?
Positive.
Positive too.
Yes.
Okay. And I get kind of confused, like with the next. Wouldn't I just like this boil this through?
Yeah, yeah.
Okay, and then the metal goes first.
Yes. The cation always goes first.
And I get kind of confused on what to do with the charges here.
Because that's 1 plus and 2 minus. This is 1 plus 2 minus minus 1. It's not balanced.
So that means that this has to have two.
Yes. Oh, not a coefficient 2. Now you're just saying I need twice of this.
So it come down here.
A substance. Beautiful.
And then,
Are we supposed to use this?
properties plus two. So that means that this is two.
Good. Exactly right.
Okay, and that's it.
And now you look for phases. What's soluble, what's insoluble.
Thank you.
And if you need to do any balancing, right? Balance the chemical equation.
Okay,
Coefficient.
thank you.
I think I know how I could have done this better. Should have made you guys Google salts. Do you know how many of you chose sodium chloride?
I don't have a phone.
Or I should have just made you come through me and Google a salt through me then. That was too many sodium chlorides. I think the other downside of this was I think a lot of you went to salts that are ions that are on the board. I get it. And a lot of the ones that are on the board are going to be soluble, no matter what.
No matter what they're paired with, right?
Yeah. Yeah.
And solubility is always AQ, right? Like,
Yep. Yeah. If it's soluble, we write it as AQ. If it's insoluble, we write it as S.
why wouldn't we just put like L for like liquid? Because when I think about solubility, I think about like something being dissolved.
It's a good question. Yes, in Monday's class, I actually started with that. I said, have you ever melted sugar? Taken solid sugar, S, and made it liquid sugar L. It's a syrup. It's really sticky and thick. Have you ever dissolved sugar in water? Is it sticky and thick? No. Is it dark like sugar is when you melt it? No. It's clear like water. So being aqueous is a different state of matter than being liquid. Do you know what temperature you need to take sodium chloride to make it liquid? Hundreds of degrees C. And at that point, it's molten salt. It's liquid salt. Have you dissolved salt in water before? Do you need to get it to hundreds of degrees C? So being a liquid is a different state of matter than being aqueous. There are different physical properties that are present. Also, liquid salt is not sodium plus and Cl minus kind of doing their own thing. Liquid salt is like, they're just able to move past each other, but they still like strongly interact with each other. Aqueous salt is sodium ion floating between water molecules, chloride ion floating between water molecules. Maybe every now and then they come by each other and then they get pushed around by the water molecules again. So being aqueous is different than being a liquid.
So sodium chloride liquid is different than sodium chloride aqueous?
Sodium chloride liquid is very different than sodium chloride aqueous.
Sodium chloride, like the one that we use in like surgery, is, I'm guessing, liquid.
Aqueous. You're talking about like a saline drip.
Yeah.
That's aqueous sodium chloride because it's dissolved in water.
We don't see like the salt floating around,
I hope not.
right?
Yeah, you wouldn't want to push solid salt into someone's veins.
Yeah.
So it's not NaCl solid, and it's not NaCl liquid. That's NaCl aqueous, dissolved in water. It's ions. It's separated. If you were giving a patient NaCl liquid, they would die. You would burn their arm off. Like if you were giving somebody NaCl liquid in surgery, your hospital would be shut down immediately. Your hospital would be a torture clinic.
Okay.
But NaCl aqueous, that's saline. That's saline drip.
Okay.
Yeah.
So aqueous just means it behaves like water then. Kind of. You can't separate oxygen.
Well, it's like, no, you can't. You don't really separate the oxygen and the hydrogen. That's a covalent bond. They're held on very strongly. But the ionic bonds also held on very strongly. Those ionic bonds get solvated. So all the polar ends of water wrap around these ions and then just pull them apart, balancing the ionic force with like tons and tons and tons and tons of dipole forces, overcoming the ionic force. So imagine screwing two pieces of wood together and then tossing it in a pool. Are those two pieces of wood going to float apart? No, they're screwed together. They're held on really tight. That's like a covalent molecule, like sugar. But imagine you've got these two pieces of wood that are like taped together, and then you toss it in a pool. Well, that tape can actually come undone. Yeah, the water kind of gets in there and ruins the tape, and then they just float apart. That's what dissolving is like. The ions just separate from each other in the water, which is different than being a liquid salt, which is super high energy.
Is this something that we can like apply, like earlier in this semester we talked about pure substances and mixtures, and we talked about how a pure substance isn't something that can be separated by like a physical means.
Yeah.
So is an aqueous solution then a pure substance?
So actually, a solution is a homogeneous. So a homogeneous mixture.
Yeah.
So if you take salt water, you can't see the salt and the water molecules. You can't separate the salt and the water molecules. It's homogeneous. but it's not pure because there are different chemicals. There are salt ions and there are water molecules. It's homogeneous mixture. You could also have a homogeneous pure solution, right? Because if it's pure, it should be homogeneous throughout. Yeah.
Yeah, that aqueous thing is kind of throwing me off. I'm just trying to like figure out
I want you to see if you can to put yourself in the perspective of a salt ion. And you've got all these other ions surrounding you, typically of the other charge. Yeah? And to become a liquid, it means that you need to be able to squeeze past those other ions, interacting with them, but kind of like moving through a crowd, you know? Pushing past one ion and then past the next and then past the next. You're never free of the ions, but you're able to move through them. Being a dissolved ion is like taking a group of people and putting them into the pool. They all swim away. Nobody's touching one another. You're all doing your own thing. That's the difference between a liquid salt and a dissolved salt. Liquid salts are pure. It's just salt. There's no water. And they're very hot, so they're able to move past one another. But they're still close to each other. A dissolved salt, there's a bunch of people in a swimming pool, and they're all just swimming around. Nobody's touching one another. No one's interacting with one another. Doesn't even need to be hot.
And that's an aqueous solution.
That's aqueous.
Just dissolve.
Dissolved. Separated.
Thank you.
All right, guys, are you ready? So I have placed your reactions on the boards throughout, and we're going to talk about some of these. So 1, 2, 3, 4 of the example reactions have sodium chloride. Can you give me one reason why sodium chloride is aqueous? Because it dissolves. Bad answer. Chloride is always soluble. Is that the only rule? Sodium is also always soluble. Chloride is generally soluble. Sodium is always soluble. Okay, so let's take this example up here. Sodium chloride and potassium chlorate. Why is potassium chlorate soluble? Alkali metal and chlorate is always soluble. What are the products formed in this reaction? Sodium chlorate and KCl, potassium chloride. I've taken the anions and I've swapped them. Saint pointed out a good method. It kind of feels like foiling. You're going to take the ion of one and combine it with the anion of the other, and the ion of the other, and combine it with the cation of the other, and combine it with the anion of the first. You're swapping those ionic pairs. No matter what sodium swaps with, it will always be soluble. No matter what potassium swaps with, the compound will always be soluble. Does the mixture of sodium chloride, potassium chlorate, forming sodium chlorate and potassium chloride, form a precipitate? Does anything fall out of solution as a solid? No. So this is actually not a precipitate reaction. We would say no reaction. Everything is aqueous. What about lithium nitrate, rubidium carbonate? What are the other products? What are the products for? Lithium bicarbonate and rubidium nitrate. Now, luckily, all of these are 1+ and 1- ions. Lithium, always soluble, so even in the product, aqueous. Nitrate, always soluble, so even in the product, aqueous. Is this actually a precipitation reaction? No, the products rubidium bicarbonate have two compounds that are always soluble, and rubidium nitrate and lithium bicarbonate. Both are ionic pairs that are always soluble. So this is actually not a precipitation reaction. Nothing occurs. Okay, and this is why I said earlier, I should have maybe given you ions to use instead of having you pick from the board, because there's a very good chance that the compounds you choose from the board will not produce a precipitate. But the exercise was still intended. I want you to be able to recognize whether it will or will not form a precipitate. All right, sodium chloride, silver bicarbonate. What are the products? Sodium bicarb, silver chloride. We know that sodium chloride is soluble because of sodium. We know that silver bicarbonate is soluble because of bicarbonate. What about sodium bicarbonate? Both are always soluble. What about silver chloride? Silver chloride is an exception to chloride solubility. So silver chloride precipitates. This is a precipitation reaction, which means now we can actually do a complete ionic and a net ionic equation. Ammonium carbonate. Why is that soluble? Not because of carbonate. Carbonates are generally insoluble. Ammonium is always soluble. Iron bicarbonate, iron 3+ bicarbonate. Why is this soluble? Bicarbonate is always soluble. What are the products? Iron 3+ carbonate, that's Fe3+ and CO3 2-. So I get Fe2, CO3 3, and then ammonium bicarbonate, that's NH4+, HCO3-. I get NH4, HCO3. Ammonium bicarbonate, soluble or insoluble? Soluble. Both of them are always soluble. Iron 3+ carbonate, soluble or insoluble? Insoluble. Carbonates are generally insoluble. And iron is not an exception to that insolubility. So this is a precipitation reaction, which means now you can do a complete ionic and a net ionic equation on it. Is that equation balanced? Not even a little bit. I'm just giving you guys the products here. I'm not actually giving them the balanced chemical equation. So ammonium carbonate, iron 3+ bicarbonate gives us a solid product, iron 3+ carbonate. Okay, what about iron 2+ nitrate and sodium chloride? What are the products? Iron 2 chloride, FeCl2, sodium nitrate. Is this a precipitation reaction? Chloride, generally soluble. Iron is not an exception. Nitrates and sodium, always soluble. This does not actually give a reaction. Sodium chloride and copper sulfate. What are the products? I should clarify, sorry, copper 2 sulfate. Yeah, go ahead. Good. Sodium sulfate. Aqueous because of sodium. Sulfates are generally soluble, and sodium is always soluble. The other? Copper 2 chloride, CuCl2. Soluble or insoluble? Soluble, because chloride is generally soluble. A precipitation reaction? No. All right, sodium chloride, calcium carbonate. Here's the deal. Sodium, always soluble. Nitrate, always soluble. So the products that form here, no matter what. Oh, no, actually, let's go through it. Sodium and nitrate, NaNO3. Calcium and chloride, CaCl2. Sodium nitrate, always soluble. Calcium chloride. Chlorides are generally soluble. Is calcium an exception? No. Here we've got Na2SO4 and KCl. We've got two group 1 cations. Group 1 cations are always soluble, so our products will remain soluble. Last group over here. Again, I've got two group 1 cations. So the products that form sodium chlorate and lithium nitrate will remain always soluble. Silver bicarbonate, sodium carbonate, gives me sodium bicarbonate, two ions that are always soluble, and silver carbonate, Ag2CO3, soluble or insoluble? Sorry? Insoluble because of? Rule 3, carbonates are generally insoluble. Silver is not an exception. So silver carbonate precipitates solid. So listen, this exercise was meant to help you predict products, not necessarily to be able to show a precipitation reaction, because that only happened like less than half the time. But even being able to say, I picked two compounds and they do not form a precipitation reaction, that's a good skill to be able to have. To say, if I mix these two salts together, will anything precipitate out of their solutions? No. That's still a good skill to have. Most of the time, though, you will be able to find a precipitate, especially in the questions that you're being asked on the homework, on the unit tests, on the exams. The skill, the real skill, is being able to predict the product of the reactions. I'll go through, by the way, but when we're done with class, and I'll kind of show those on the video so that they get put up onto the recording. Okay, do you guys feel a little bit more confident predicting the products of precipitation reactions and deciding whether they follow these rules or not? Okay, that's what we need. We're going to move on to our next class of reactions. And thank you guys for putting up with me. You guys know that I'm in that education class, learning how to be the best educator I can be. And they say that having students get up and move around and do work actually increases your learning. This is why I'm having you do that weird exercise where I put you into pairs. We'll see if it works, huh? Okay, reaction type number 2. Acid-base reaction. There are many definitions of acid-base reactions. We are going to focus on one of those definitions. These are reactions that produce water and a salt. For those of you that are curious, We have Arrhenius acid-base reactions, Bronsted-Lowry acid-base reactions, and Lewis acid-base reactions. And we are looking at this type, the Bronsted-Lowry acid-base reaction. Arrhenius defines acid and base as in water, they produce hydronium and hydroxide. Lewis defines acid-base as electron pair donor, electron pair acceptor, and Bronsted-Lowry is right in the middle. It says hydrogen ion donor, hydrogen ion acceptor. That's all that we're really looking at. It's a little confusing. It's actually, if you drew a Venn diagram of these, Lewis is the biggest, Bronsted-Lowry sits inside of it, and Arrhenius sits inside of Bronsted-Lowry. So this is the most narrow definition of acid-base. This is a bit broader, and this is the broadest. We're focused just on the Bronsted-Lowry. So in general, we're going to be looking at a generic reaction that says acid reacts with base, and these are going to be aqueous solutions to give liquid water and a salt. That salt does not need to be soluble. It can be aqueous or solid. So I don't really know how you want to show that. I'm going to put this aqueous / solid. It may precipitate, it may not precipitate. That's not us. That's not necessarily the concern. We now have the rules to decide whether that's true. If we were to take these apart, though, acid reacts in water to give a hydronium ion, that's H3O+, and what we call a conjugate base. Some people will show acid as HA. An acid is a source of H+, which means the conjugate base is after it's given H+ to water, we get A-, the conjugate base. For example, hydrochloric acid, HCl, produces H3O+ and chloride, Cl-. The base runs just the opposite. First, though, I want to give you two types of bases, acids. If an acid is defined by giving its hydrogen to water, dissociating, if you will, then a strong acid is one that does that really well. All of the molecules of a strong acid give away their hydrogens. If I have 1 mole of HCl, a strong acid, no, I don't. I have 1 mole of H3O+, and 1 mole of Cl-. They completely dissociate. That's a strong acid. Here are our strong acids. There are different ways to remember them. This is how my Gen Chem professor taught me, and it works really well in my opinion. Bic pens. You guys know Bic pens? Who's got a Bic pen on them right now? Great. This is spelled a little bit wrong, right? Bic pens with 2 C's. That's helpful because it's going to remind us that there are two acids that have C in it. You'll notice that Bic pens actually has P and E together. That's really intentional as well. A lot of these can kind of be determined by the letter that is with inside of the element. But P, if you left P alone, you're going to think phosphoric acid, and phosphoric acid is not on here. So here's B. B is HBr, hydrobromic acid. I, HI, hydroiodic acid. Given the first two, can you guess the third? Do you think C stands for carbon or chlorine? Chlorine. We're in this family. Bromine, iodine, chlorine. Hydrochloric acid. C is actually never going to stand for carbon. Carbon is a terrible acid. Then the second C is a second chlorine. If not HCl, hydrochloric acid, we actually get chloric acid. HClO3. Remember, chlorous acid is HClO2. Ite becomes us. Ate becomes ick. PE. Any guesses? It's one of our per ions. Perchloric acid. HClO4. Do you see how that PE actually helps remind you that you're going to have a per acid in there? A peroxy acid? Perchloric. Okay, now N and S, they actually do remind us of our elements again. Any guesses for N? Nitrogen. Nitric acid, HNO3. Not nitrous acid. And S? Sulfuric acid, H2SO4. Can you tell me what sulfuric acid, what makes sulfuric acid stand apart from all the other acids? Sulfuric acid has two hydrogens. We call this a diprotic. Protic? The heck is protic trying to say? Protic, related to the word proton. What's a proton? A proton is a hydrogen ion. And honestly, if that doesn't make you lose sleep at night, good for you. I lose sleep thinking about that. The hydrogen ion is just a proton. You know what else has protons, right? All of the nuclei. Carbon has 6 protons. Iron has 25 protons. Hydrogen has 1 proton. No neutrons. Take away hydrogen's electrons, and it's just a proton. So when we say that an acid is this H plus donor, and then it gives a hydrogen ion to water to make hydronium, we're saying it's a proton donor. It gives just a proton, H plus. Okay, that's all. Take it or leave it. If we have strong acids, it implies the existence of weak acids. Earlier I said that if you had 1 mole of HCl in water, you don't. You have 1 mole of H3O plus and 1 mole of Cl minus. They completely dissociate. Weak acids, if you have 1 mole of a weak acid, they'll partially dissociate. So you might have 0.1 moles of H3O plus and 0.9 moles of the original HA, the original acid. That is to say, a very small number of molecules of the acid will actually act as an acid. If an acid's job is to give its hydrogen to water, weak acids are very bad at doing that. Very few of them give their hydrogen to water. Which of our acids are weak acids? All the others. Carbonic acid, nitrous acid, sulfurous acid, chlorous acid, hypochlorous acid, carbonic acid, phosphoric acid, all of acetic acid. All of these are considered weak acids. We can actually even write this. If you take acetic acid, C2H3OH, you can say that plus water, sorry. We can say that some of this acts as an acid to give C2H3O2 minus plus H3O plus, but a much larger amount of it remains as acid. It's Gen Chem 2 where you'll actually talk about those ratio of the ions. We call it a dissociation constant, the ratio at which they prefer to be separated. But here's a general number. For every 1 billion molecules of acetic acid, about 1 of them gives away its proton. And that number can range anywhere from 1 in a billion to 1 in 10 billion to 1 in 100,000. Those ratios are huge, but they're all generally considered weak acids. Not a lot of the ions give away their hydrogen. Okay, those are our acids. In terms of bases, if we have a base plus, well, okay, hang on. I'm going to rewrite this. Now, here's how I want to say it. Bases generally contain hydroxide ion. Hydroxide is what we often refer to as our best base. We could write a similar equation. What does the base form when it reacts? But if hydroxide is in solution, then what it often looks like is base, some B, mixed with hydroxide, will dissociate into base plus and hydroxide minus. That's the dissociation again. Similar to how the acid dissociates, but it gives its proton to water. Here, it can't give a proton to water. And if it reacted with water, it just produces hydroxide. So this is the best way for us to write it. What would this be called? B plus. If HA is an acid and A minus is a conjugate base, BOH is a base B plus would be a conjugate acid. Do you guys know what conjugate means? Any of you guys take language classes and have to learn how to conjugate your verbs? Taking the same verb and then just writing it in different forms? That's a good way to think about conjugate acids and conjugate bases. You have a chemical and now it changes forms so it actually can behave differently. A base becomes a conjugate acid. An acid becomes a conjugate base. All right, and then again, we've got strong bases and weak bases. We have a much easier time remembering all of our strong bases. That's group 1 hydroxides plus group 2 hydroxides. That is, if the group 2 hydroxides completely dissolve. Remember, only some of the group 2 hydroxides completely dissolve. So we get things like lithium hydroxide, sodium hydroxide, potassium hydroxide. These are some of the most common strong bases that you'll interact with. Then you get things like magnesium hydroxide. Notice the chemical formula changes because group 2 ions are 2+. Calcium hydroxide. Barium hydroxide. These are some of the most common strong bases you'll see from the group 2, except I need to cross one of these out. Based on our solubility rules, I erased it. Solubility rule number 4, one of these group 2 hydroxides does not dissolve well. Calcium hydroxide dissolves. We say that hydroxides are generally insoluble. Calcium hydroxide is an exception to that rule. Barium hydroxide, an exception to the generally insoluble. Magnesium is not an exception. Magnesium hydroxide it doesn't dissolve well. If it doesn't dissolve well, then it's challenging to make it act as a base. All right, now that equation that I showed you earlier, acid plus base reacts to form water and salt, that's better known as the neutralization reaction. We talked about this chemical reaction on Monday. Vinegar and baking soda, acetic acid, C2H3O2H, reacts with sodium bicarbonate, and we can make these both aqueous solutions, aqueous acetic acid, aqueous sodium bicarbonate. I picked a bad example, actually. Sorry. These are going to form sodium acetate, Na, C2H3O2, always soluble, aqueous, plus acetic acid comes with bicarbonate to form H2CO3 aqueous, but bicarbonate doesn't exist long. We talked about this earlier in the semester. Bicarbonate will, when you crack open a soda, bicarbonate decomposes into water and CO2. So here's that water that I get. Here's the salt that I get. On the worksheet that I gave you guys last week, or last class on Monday, the backside is actually predict the product of acid-base reactions. I want to go through the first one with you guys. Let's take barium hydroxide and hypochlorous acid. Can anybody give me one of the products formed in this neutralization reaction? Okay, we went for the harder one. Barium hypochloride. Hypochlorite is a 1- ion. We can prove that because it's balanced with an H+ just once. And barium is a 2+ ion, so I get barium ClO2 plus water. Where does the water come from? It's H+ and OH- becoming water. Is this chemical equation balanced? What coefficients can I add to balance it? I need a 2 in front of HClO because I need 2 of those hypochlorite ions. Won't be it. I've got 2 hydroxides, 2 H+s. That forms 2 waters. You can think of this water as being that hydroxide that has reacted with the H+ from the acid. They don't behave like this. I'm sorry. It's not an ionic bond, but that's where they form from. They come together to give you water. So if I have 2 hydroxides, I'm making 2 water molecules. That's as easy as it is. So you guys need to predict the water and the byproduct salt in these 3 reactions. Now, I've taken you over time. I apologize. Thank you for your time. On Monday, we'll look at our 3rd class of reactions. And from there, we'll move on to stoichiometry. Have a good weekend.
I will tell my lab partner too.
Good idea. We did this exercise in class today, but I said that I would